Welcome back, Algebra 2. Let's take a look at our first example today. It says use the exponential curve below to estimate A, the number of bacteria after 1 hour and 15 minutes, and A again, I suppose. Let's change this to B. B, the time where 1,500 bacteria were present. So, all right, let's deal with letter A here first. The number of bacteria after 1 hour and 15 minutes. That means if we're reading our graph here, we need to say, okay, well, first of all, we have to identify what our axes are here. This first one is your time in hours, and that would be our x-axis, of course. And our y-axis is going to be representing our bacteria. So, taking a look at each axis, if I want to know the number of bacteria after 1 hour and 15 minutes, well, I would look on my time axis and find where 1 hour and 15 minutes is. Now you have to be careful here with your scale. So essentially this is 1 hour for every second hash mark here. So half of that would be half an hour. So then everywhere in between that would be 15 minutes. So we have 15 minutes, 1/2 of an hour, 45 minutes, and then 1 hour. So then our next one would be 1 hour and 15 minutes, and then an hour and a half, then an hour and 45 minutes, then 2 hours, etc., etc. So if I want an hour and 15 minutes, that would be at this hash right here, and then we'd go up to our graph, drawing as straight of a line as we possibly can. Maybe you can use the edge of your paper or something of sorts. Hopefully you've drawn this graph down, because that's what I will be looking for tomorrow. And then once you hit that, you go straight up to the graph, and once you hit that point, well, that'll tell you how many or how much bacteria you're going to have. So then you go straight to the left to your bacteria axis, and that'll give you an idea. Of course, it's not exact, but an idea of how many bacteria there were. So then we have to read our bacteria axis and see what it's being scaled by. So since this hash mark is 400, well, half of that at this first one would be 200, making this guy right here 600. So if we're between 600 and 800, well, this guy right here must be around at least the 700 mark. So our answer to letter A would be 700 bacteria. Okay, so you always want to be careful of your scales, because they're obviously not even the same. Okay, this is scaled by 200s over here, and then on the bottom we're scaled by 0.5, so that's two very different scales there. Okay, so letter B then, it says the time when 1,500 bacteria were present. So they actually tell us how many bacteria we're going to have this time. So we find that on our bacteria scale. So we're kind of doing the same thing, only backwards here. So remember, we're scaling these each by 200. So we're at 1,200 here. So that would mean this is 1,400. And then the next one is 1,600. So between 1,400 and 1,600 would lie our 1,500. So right in here for 1,500. So we follow that out as straight. Whoops, sorry. Follow that out as straight as we can out to our graph. I know I have a little bump here, but straight as we can. There we go. That's a good one. And then once we hit our graph right there, we go straight down. As straight as we can. Alright, so it would be between, I would say, you know, we're a little bit above that halfway mark right there. So if you said 2 hours, sorry, I don't know why that keeps popping up. If you said 2 hours and 15 minutes, I wouldn't be that mad at you. I'd take anywhere between 2 hours and 15 minutes. And maybe 2 hours and 20 minutes would be another acceptable. So 2 hours and 20 minutes. Okay, so either of these two answers, or really anywhere in between there. If you said 2 hours and 18 minutes, I wouldn't be that mad at you. If you did say 2.5 hours, yeah, that would be wrong, because we're obviously not on this line right here. And this would be our 2.5 hour mark, because that would be 3 there. So either one of these answers, I like 2 hours and 20 minutes, so I'm going to box that one up as my answer. But if you want to put 2:15, be my guest. Okay? So just a little bit about reading graphs, and notice this has our exponential shape again that we're looking for. One thing I don't like that this software doesn't do, sorry, is put little arrows at the end of your graph, because it doesn't just stop there. It keeps going on in either direction. And one other thing too, you're going to see tomorrow in your packets is when you're doing exponential growth, you never are going to have this piece come down and actually hit your x-axis down here. Sorry. So if I extend my x-axis out, this piece will never cross. It'll keep getting closer and closer and closer, but it will never come down like this. So when you're drawing your graphs, do not draw that piece down there, because that'll never happen. And once we talk about exponential decay, it'll become a little more clear as to why it never hits. And if not, I can demonstrate something in class for you that kind of makes it a little more clear as to, hey, this is going to hit the x-axis or it's not. Anytime it's any kind of exponential, either bacteria, either growth or decay, it's actually never, ever, ever going to hit that x-axis. So that's one thing I want you to remember about these graphs as well. Okay, example 2 says, in 1993, the population of the U.S. was about 258 million. During the early 1990s, the population of the U.S. was growing at a rate of about 1% annually. Suppose this growth rate continues. Let P of X equal the population X years after 1993. So it says find a formula for P of X. So what we're going to do, and this isn't our answer here, I'm just going to write our exponential growth model over here. Remember, it was f of x equals a times b to the x power. And if you remember correctly, a was our initial amount, or if you want to look back in your notes here real quick, that's fine too. And then b was our growth rate. And, rate with an E, okay. This X really is time here. I didn't put that on our last slide, but it's not always going to be time, but typically, 99 times out of 100 it is going to be time here. So we're going to use this model and plug in numbers where we can. And this we're going to have to do something a little special with, and you're going to see here in a second. So our formula for P of X, we're going to just change F to P, which is no big deal. We're allowed to do that. So P of X equals, and then we're going to read what we've got over here. Well, do I have an initial amount? Well, our initial amount is what we started with in 1993. So what we started with in 1993 was 258 million. Now, you have a choice here. You can write that number out, which would be 258, and then million would give you 6 zeros. So you can write that out if you choose to. I'm actually going to skip that, and as long as I use this unit as million when I'm done, I can use the 258 and just do my calculations with that, which I like a lot better than messing with this number up here. So I'm just going to put 258 and just remind myself at the end that, hey, we're in millions. Maybe write it off to the side, so say millions, just to remind yourself. Okay, so 258, and then we say times our B, which is our growth rate. Okay, so now our growth rate is 1%, which pay very close attention to what I'm about to say, because this is something that is difficult for some people to grasp here. There's actually two things that we need to remember here. The first thing being, are we allowed to just put 1% in there? No. So we're going to have to change that to a decimal here in a second. But I also want you to think about this formula working as, we don't want to have to add it back to the original population. So for instance, if we take 1% of our 258 million, that would be 2.58, okay? So 2.58, then you would have to take that 2.58 and add it back to the original 258 million up here. So then we have to have, oh, okay, we have a plus stuff over here, so that's, we don't want to have to worry about that. So what I want you to think about is percentages. So it's growing by about 1%. Now, forget this 258 because it doesn't matter what it is. If it's growing by about 1%, we're adding that back to our original population, which accounts for 100% of the original number we had. So instead of saying our growth rate is 1%, because then we're only taking that 2.5, we're going to say it's 100%, so that we're taking that 2.5 plus our original 258. So really what you want to do here is take 1 plus 100%, giving us 101%. It's like, a population is kind of a hard thing to think about, but if you think about a sales tax, okay, and you wouldn't have 1% sales tax, let's say you have 6% sales tax. And let's say you go into a store and you're buying a bracelet that costs, let's say, $100, okay? So if it costs $100 and there's 6% sales tax, obviously your sales tax is going to be $6, okay? Now, is the sales clerk going to ask you for $6 to pay for that bracelet? No, they're going to ask you for $100 plus $6 to pay for that bracelet. So they're going to add it back to the original price. Now, if we just say that 100% of the original price was $100, so 100% of the original price was $100, so then we would have 106% because we'd have to add that 6% sales tax right on in there. Okay, and that would take care of for whatever price that it was. So $100, $200, $300, it doesn't matter. As long as you add it back to 100%, which was the original amount, doesn't matter what the original amount was, we're adding it back to 100% of it, then we're going to get an accurate form here. Okay, so always add it to 100%. And if that confuses you a little bit, make sure you ask me about it tomorrow, because it's something that's tough to kind of wrap your head around. Okay, and then our very last step here is we don't want to use 101%. We want to change it to a decimal, which we know it's always got to go 2 places. So 1, 2 places gives me 1.01%, or excuse me, 1.01, not percent anymore. So 1.01 is our growth rate. After all is said and done, just remember you got to add 100 to it and then move the decimal point over 2 places. Okay? Now this time thing here, normally we just put in an X there, but we need to figure out how many years after 1993 it is. So we want to say X minus 1993. So for instance, if we had 1995, we'd do 1995 minus 1993 and we'd get, oh, well, we'd get 2. Okay, so you can set it up like this, or if you just want to put X and then remember that it has to be since 1993, you can think of it that way too. Okay, I like to have it in my formula. So this whole thing, believe it or not, is our formula for our population. Okay, all right, so what would the population of the U.S. be in the year 2013? Well, all we have to do is say, okay, well, what is P of 2013? And guess what? That's this year. So we're actually going to figure out what our population should be this year. So we would say, all right, we're just plugging it into this guy here. So we have 258 times 1.01. And then our whole exponent is going to be 2013 minus 1993. And then my suggestion would be at least simplify this before you go to your calculator. So we have P of 2013 equals 258 times 1.01, and then very easily 2013 minus 1993, that would be 20, so we'd have to the 20th power here. Okay, so 20 years have gone by. Now at this point, please follow order of operations here. So we have to do this part first and then multiply it by the 258. So let's grab our calculators. Hopefully you have yours as well. Now you can do this one of 2 ways. You can do order of operations, which is what I like to do. I like to do 1.01, whoops, let's try that over, 1.01 to the 20th power, hit enter. That's actually our growth rate. We're growing by 1.22% over these 20 years. And then we're going to multiply it by our original amount, which is 258. And that's our total population. Now remember, that's in millions, so it's not just 314 people, it's 314 million people. Now, if some people like to just put this whole shebang in their calculators, it will work for you. You'll have 258 times, if you do it right, of course, 1.01 to the 20th power. And then we hit enter, and guess what? We get the same darn answer. So let's go ahead and write it down. So we're going to say P of 2013, because that's the population in the year 2013, is 314.8, we'll just say 8.8 billion, no, I'm sorry, we were in millions, million people. Sorry, I got a little carried away there. Just million people. So the population in the year 2013 should be 314.8 million people. Now, that was back in 1993, and, you know, maybe a little later 90s, because they figured out what the growth rate was in the 90s. So back then they estimated there'd be 314.8 million people. Well, guess what? It's the year 2014, and let's see how many people are actually in the U.S. So we would say, hang on a second. I Googled it. Sorry, I went too ahead. I Googled it, and the U.S. Census Bureau says, well, it's 313 million people. So we were actually pretty darn close. And that's the beauty behind mathematics, is that we could use that model to predict these things. Now, why would you want to predict such a thing? Well, hang tight and I'll talk about that in the very next video.